Okay, let's dive into this. Ever wonder what's really powering our world? I mean, beyond just the obvious stuff like electricity, there's this invisible backbone to our daily lives running everything from the gas stove in your kitchen to the scooter on the street. And we're going to break down exactly what it is: hydrocarbons. Think about it for a second. The LPG cylinder that your mom uses for cooking, the petrol you fill up in your bike, or even the plastic bottle of water you're holding. What's the hidden link between all of them? Well, it's a huge family of molecules called hydrocarbons. And trust me, once you see them, you'll start seeing them absolutely everywhere. Now, to really get a handle on this massive family, you need to know about the one big divide that splits them right down the middle. This isn't just some boring category, it's the key to their entire identity. We're talking saturated versus unsaturated. This one single difference dictates all their chemical behavior, basically how they interact and play with other molecules. So what exactly are they? The name pretty much gives it away: hydrocarbons. They're just compounds made of only two things: hydrogen and carbon atoms. That's it. Such simple ingredients, but they literally build our entire modern world. It's kind of wild when you think about it. Okay, so here's that big divide in a nutshell. Just focus on the bonds. On one side, you have the saturated guys, the alkanes. They only have single carbon-to-carbon bonds. Think of them as chemically stable, happy, unbothered. But on the other side, the unsaturated molecules have double or even triple bonds, and these bonds contain a weak link, a pi bond, that makes them way more reactive and always ready for some chemical action. So how does this stability actually play out in a reaction? Well, a saturated alkane is kind of like a full bus. Every single seat is taken. If a new atom wants to get on, sorry, but another atom has to get off first. It's a strict one-for-one swap. And in chemistry, we call that a substitution. But the unsaturated molecules? Totally different story. That weak pi bond is like an open invitation, a welcome mat for other atoms to come and react. New atoms don't need to kick anyone off the bus. They just break that weak bond and join the party. It's an addition, not a swap. There's plenty of room for more. You see? This one difference in their structure creates a completely different chemical playbook for each type. So let's actually see these two plays, the swap and the join, in action. First up, the stable alkane. Let's take methane, which is the main gas in CNG. It meets chlorine, but only in the presence of sunlight. That light provides the energy to force a reaction. A hydrogen gets knocked out, and a chlorine atom takes its place. It's a classic swap, a substitution. Simple as that. All right, now for the reactive alkene. Watch what happens here. You've got ethene with its double bond, and it meets some hydrogen. That weak pi bond eagerly just breaks open, and boom, the two hydrogen atoms are added on. The double bond completely vanishes, becoming a single bond. Just like that, ethene has transformed into ethane. It's a totally different game. And you know what? This actually reveals a really simple hack for figuring out these reactions. Whenever you see an unsaturated molecule with a double or triple bond, don't overthink it. The whole game is just to break that weak pi bond and add the new atoms right on. It really is that straightforward. So we just saw an alkene turn into an alkane. And that brings up a really interesting question. How do chemists actually build these molecules on purpose? Let's take a quick look at two common ways they prepare the stable alkanes. The first method is something we've basically already seen. You just start with an unsaturated molecule and add hydrogen to it. That's called hydrogenation. The second method is a really clever trick called the Wurtz reaction. Basically, it uses sodium metal to stitch two smaller carbon chains together to make a bigger one. It's another neat way to build those stable alkanes from smaller pieces. Okay, so just when you think you've got the rules down, saturated is stable, unsaturated is reactive, along comes a molecule that seems to just break all the rules. Let's talk about benzene. So here's the puzzle of benzene. Just look at it. It's a ring of 6 carbon atoms, and it has 3 double bonds, so it looks incredibly unsaturated, right? By all the rules we just learned, it should be super reactive, just jumping at the chance to do an addition reaction. But it's not. It's surprisingly stable, and it actually prefers substitution reactions, like the alkanes. Why? What's going on here? The answer lies in this really cool property called aromaticity. It's a special kind of stability that only certain ring-shaped molecules can have, and it's all about how their pi electrons, those electrons from the double bonds, are arranged. This special stability is governed by a little checklist called Huckel's rule. So the molecule has to be a flat ring with a special electron loop. But the most important part, the real secret code for this stability, is that last point. The number of pi electrons has to fit a magic formula, 4n+2. So let's run the numbers for benzene. It has 3 double bonds, so that gives it 6 pi electrons. Does 6 fit the 4n+2 rule? Yep, perfectly, if n equals 1. So here's the secret. Because it fits the rule, those 6 electrons aren't stuck in 3 separate bonds. They're what we call delocalized. They're shared equally all around the entire ring, kind of like an electrical current. And this sharing is what gives benzene its incredible, unexpected stability. So, after diving into all these rules and exceptions, let's pull back and ask the big question. Why does any of this chemistry matter? Well, it's not just theory in a textbook, it literally shapes our entire world. So why does it all matter? At the end of the day, it comes down to energy. Look at this chart. A double bond holds almost twice the energy of a single bond, and a triple bond holds even more. When we burn these molecules as fuel, we're breaking those bonds and releasing all that stored energy. That energy release is what cooks our food and powers our vehicles. The type of bond literally dictates the power. And their impact is just massive. Hydrocarbons are our #1 source of energy. They're the building blocks for almost all plastics. We're talking everything from polythene bags to your kids' toys. They're essential in industry for making paints, medicines, you name it. But there's a flip side. Some of the more complex hydrocarbons can be really toxic, even carcinogenic, causing serious health risks. So you see, these simple molecules, made of just carbon and hydrogen, are a true double-edged sword. They build and power our modern society, but they also pose some very real dangers. Their story is really the story of our industrial age. So the final question is, as we get smarter and better at manipulating them, what will they build or break next?